I want to try and get to the bottom of what that is, and then what the challenges are for why we don't actually have quantum computers yet, because obviously we want to have them, but we don't. We have normal computers and we've had them for quite some time. Why is that the case? And so, and then finally, where are we at now, and what's the likely next few steps for that evolution of the technology? So this is classical physics, Newtonian physics that we all learn in high school, and we can talk about the state of an object as being really just a mathematical description of everything about an object, for example. So if we've got this apple, then in Newtonian mechanics, that apple can be fully described by things like its position and its velocity, how fast it's going, which direction it's going, the rate at which it's rotating. And all of these things are really, really well defined. The position is well defined, and if you know the position, that doesn't inhibit you from knowing what its rotation is or what its velocity is. And they're very, very precisely defined. They're completely certain. If you measure an apple, you know exactly where it is, and the same with any other classical object. But that's a fundamental difference to quantum physics, where none of those statements that I just made are really quite true anymore. We'll come back to that in a second, but based on this underlying idea that in classical physics everything is really, really well defined, we can then define the idea of information. If physics is well defined, you know, position, velocity, things like that, we can use that to represent information. So if we wanted to represent information using apples, we could say that if the apple is sitting to my left-hand side, that represents a 0, and if it's sitting to the right-hand side, that represents a 1. And that's really what binary information is. You just have different classical physical systems with different states. In this example, apples, but it can be anything, and they represent units of information. But in actual circuits that we have today, we don't use apples, we use electrical circuits where different voltages or currents represent the 0s or 1s. So if I have a particular voltage level in a wire, that represents a 0, and if I have a different voltage level, that represents a 1. That's the basis for classical computing. But just like the position of apples, the voltages of electrical signals are also well defined. They have a specific well-defined value. And from that, then you can go on and build computers. Once we know how to encode information using a physical system, then we have the idea of using gates, which is what all of our integrated circuits do today, to manipulate these bits to evolve them and give us the output of a computation. So if you've ever done any electronics, some of these things will look very familiar. So over here on the left, we've got different types of gates. So this one here is called an OR gate. The idea is that the output here will be 1 if either of the inputs are 1. Or both of them are 1. The AND gate means that the output is 1 only if both of the inputs are 1. The exclusive OR gate means that the output 1 is 1 if exactly one of the inputs was 1. So it was either 1 and a 0 or a 1 and a 0. A NOT gate flips the value of a bit. So a 0 becomes a 1 and a 1 becomes a 0, and so on. And using these gates, we can combine them together to build up arbitrary logical circuits. And there's this notion in classical computing of universality, and that is that using a finite number of set of gate elements, so in this case, if I have NOT gates, AND gates, and OR gates, just any combination of those three combined in the appropriate order, I can implement arbitrary digital transformations. So they form what are called a universal gate set, OR, AND, and NOT. So if I have a bunch of bits, then some combination of those can do any computation at all. And what our integrated circuits do today, they want to do arbitrary computations, not a fixed one. So they combine these in a reconfigurable way so that they can be dynamically reconfigured. And then you use your programming languages, whatever you're familiar with, to basically go in using a human readable form and compile it down to machine code, which basically controls what sequence of those gates are applied to your input digital sequence. And that's the basis for how our modern computers work and why they can effectively implement any algorithm whatsoever. Now, in quantum physics, we can also have the idea of bits. If I have a quantum system, and so a quantum system, as I'm sure you know, really just refers to things really down at the very, very small particle level. It can be atoms or photons or electrons or any sort of elementary unit like this. We can also use the states of those particles to define bits of information. So here, for example, I've got an atom, and just like the apple, if I say it's on the left, I can associate that with a logical 0, and if it's on the right, I can associate that with a logical 1. I can do that just like with apples. The difference is that with quantum physics, things can also be in superposition. I promised no mathematics, but here's one piece of mathematics, the plus sign. Quantum physicists use the plus sign to represent that things are in superposition. So mathematically, that would represent a superposition. In other words, a state where the atom is both in that first position and that right-hand position at the same time, which is a phenomenon that you don't get with classical physics. If it's the apple, it's either one or the other. With the atom, it can be both at once, but it can also be an arbitrary combination at once. You could say that it's 90% on the left and 10% on the right. And this is called the quantum amplitude, which is to what extent is a particle or a quantum state in these different fundamental states. And that extends generally beyond just two states, the way I've drawn it here, but you could have an arbitrary number of states and then an arbitrary superposition of those states. Now, the second problem of quantum mechanics is the measurement issue, and that is that if I have an atom like this, which is in a superposition of being here and here at the same time, if I then go in and look at it with a very, very high resolving microscope, you won't ever actually see the atom in two places at once. That's not physically possible. You only ever see an atom in one place or another, just like the other, just like with the apples. The reason for that is because when you measure a quantum particle that's in a superposition, it undergoes what's called wave function collapse, which means that if it's in a superposition, it then reduces down to being one or the other, and is no longer a superposition. And then the superposition terminates because the measurement has destroyed the superposition. And the rule for how it goes about collapsing is a random one. So if I have a 50-50 mixture of this 50-50 superposition of this one and this one, then if I measure it, then with a 50-50 probability, I'll see it either on the left or on the right. And similarly, for those different amplitudes, they reflect the probabilities that I'd get up on measuring those atoms are. So quantum information is built upon this idea of associating quantum states with elementary particles like this, which are in superposition form. The trouble is that if I go in and measure it, then it looks like digital information where it's just one value or the other. The superposition disappears. And that's actually turns out to be a bit of a complicating feature, which we'll come back to in a second. Now, this plot down the bottom, this is called an interference experiment. So this horizontal bar here that represents just a piece of paper that blocks light, and there are two little gaps in there. And if I put in some laser light coming in from the left, then just like water waves, it starts coming out these two slits, and the wave fronts start interfering. As you can see over here, you get points of constructive interference and points of destructive interference. You can see this in the bathtub. If you just make two waves on the surface, you can see the points where they interfere. And then if you measure them at the output here, you see this, this interference pattern. Now, that's what you get with laser light. What's remarkable is that if instead of putting in laser light, I put in just a single photon here, which is an indivisible unit of light, I will see exactly the same interference pattern over here. So even though this interference pattern relies on the fact that that there are two different wave fronts here interfering with each other, giving constructive interference, I still observe that interference effect if it's just a single indivisible particle. And that's because what actually happens is that that single photon goes into a superposition of going both ways at once and then interferes with itself on the other side. And so this simple experiment, when you do it with a single photon, provides a simple proof that an elementary particle can in fact be in superposition and can interfere with itself, and that demonstrates in a really elementary way this notion of superposition of an indivisible quantum particle. So now coming on to quantum information. Instead of bits, we want to have quantum bits, or qubits we call them. So just like with digital classical information, we choose a physical system that has two levels or two states, and we just call one of them 0 and another one of them 1, just like with digital information. But now the difference is that the qubit can be a superposition of both. Now, if I have one qubit, that means that it could be 0 or 1, just like a classical bit, but it can also be some arbitrary combination of those two given by different amplitudes. But if it's two qubits, then it could be 0, 0, or 0, 1, or 1, 0, or 1, 1. Those are all of the four possibilities. And for classical digital information, it can be any one of those four possibilities. But with the quantum information, now it can be an arbitrary superposition of all four of those possibilities. If I have 3 classical bits, there are 2 to the power of 3, which is 8 combinations, but I can only have one of them at a time. With qubits, now I can have a superposition of 8 combinations at a time. And this generalizes, as you'd expect, using this exponential. With n qubits, there are 2 to the power of n different combinations. So in a classical digital system, if there are 100 bits, you could have one of any of 2 to the power of 100 bit combinations, but only one at a time. Whereas with our qubits, we could have 2 to the power of 100 all at once. And that grows really, really, really quickly. And to put things into perspective, 2 to the power of 200 is roughly equal to the estimated number of atoms in the visible universe. So these exponentials grow astronomically. And so with 200 quantum bits, each of which can have a logical value of either 0 or 1, in principle, I can have a superposition of more combinations of logical states than there are atoms in the universe. Of course, 200 particles, that's not actually that many. That's still a pretty tiny system. So we're starting to begin to get a flavor of where this power of quantum computing might be coming from. It's because of its ability to hold these different states in this highly elaborate superposition of all these different states at once. So the idea of a quantum computer is just like with a classical computer. We want to process information, but now we want to process information that's in a superposition form. So instead of classical information where it's always one value at a time, now internally within the quantum computer, it's going to be some big superposition, and the computer needs to be able to manipulate these superpositions, not just single states of information the way a classical computer does. But what that means is the output is also a superposition. So a common misconception then is that, well, if a quantum computer can operate on things in superposition, why don't we just make a superposition of all possible input values to a computation, put them through a quantum version of the same classical algorithm that we'd normally apply it to, and then at the output we'd get a superposition of all of the possible output state, of all of the possible computations. And you can certainly do that. And people think, oh, well, that means that what we can do is we can effectively get the answer to all possible evaluations of a computation at once. But it doesn't actually mean that, because remember I said earlier on that we don't see things when we measure them. We never see superpositions. They collapse down. So if I give you the output to a computation, which is a superposition of all possible computations, as soon as I measure it, it collapses down onto just one of them, and it does so randomly. And so we only actually get the answer to one evaluation of the computation, which is exactly what the normal classical computer would have done in the first place. And so you'd look at that and say, well, that makes it sound like quantum computing is useless. It effectively does all this incredibly complicated stuff internally, but as soon as I measure it, I'm only capable at best of getting the output that I would have got from asking a classical computer the same thing, which is the answer to one evaluation. And so that's really the underlying reason why there's a lot of subtlety and nuance to the way quantum computers work. It's not just a simple case of you pump in this superposition of everything, you get the answer to everything. This measurement problem, because we have to measure things, because otherwise we can't get an answer to anything, that makes things really, really nuanced. And the trick here is to use interference, like what I showed earlier on with that photon interfering with itself, to make different components of these superposition interfere in different ways, so that even though I don't get the answer to all of the outputs at once, what I can do is somehow extract some kind of useful global property of all of them at once. So you might be able to get an answer about what's like some sort of average property of all of those computations, for example, something along those lines, as opposed to what are all of the individual answers. So here's what the way quantum computer scientists sort of think about quantum computers. I showed you what the classical digital circuits look like that are probably very familiar to you. And just like in classical circuits, we also have quantum circuits, very much the same, which have quantum gates, like with classical circuits, and we combine those together to build up quantum circuits. This bottom down here is what a quantum circuit looks like. So over on the left, you've got some input quantum states. So this could be our zeros or our ones or our superpositions. These down here represent single qubit gates. So things like the NOT gate, for example, that flips a 0 to a 1, but it can do more elaborate things like switch the amount of amplitude between 0 and 1. This one here is called a controlled NOT gate. And what that does is it says that if the value down here is 0, then it flips the value of the one up here. Sorry, other way around. If it's 1 down here, it flips the one up here. And if it's 0, it does nothing to the other one up here. These ones here, these represent measurement devices. So this is where we come in and we measure a qubit and we want to know what the output is, and then it converts the superposition and collapses it down onto a particular value to give us our output. And just like with classical circuits, there's the idea of a universal gate set with a very specific set of gates. You can combine these arbitrarily to get an arbitrary computation. Unlike classical circuits where you have sort of arbitrary layout, in this particular quantum circuit, time always strictly evolves from left to right. There's no feedback loops the way you can have in classical circuits. So that's one of the fundamental differences. But apart from that, it's conceptually very, very similar, and we can just build up a big computation like this. But that's sort of represented in a very abstract way, where I just talked about qubits, and you remember that qubits can be represented using different types of quantum systems. There's no unique way to do it. Just like with a classical bit, I can represent a bit using an apple, or using an electrical signal, or using my hands, or using something written on a piece of paper. With quantum computers, it's exactly the same. You can choose any kind of quantum system to represent your quantum bits. So up here, this is the type of work that I do, which is optical quantum computing, where you have light coming in, where single photons encode information. So a superposition of a photon between two different optical waveguides represent a quantum bit. So here, this could represent a logical 0, and this could represent a logical 1, or I could have a superposition of the two. And then in the middle here, we've got what's called a beam splitter, which makes them interfere, and that implements simple transformations on this bit of logical information. But the optics isn't the only way to do it. Another way to do it is using superconducting rings. So we all normally think of electrical circuits as being defined by currents and voltages, which are classical and well-defined. But if you go down to the quantum level, they can actually be in superposition too. So if I make a really small superconducting ring like this, with current circulating around it in a loop, I can actually define a logical 0 as being the current flowing in one direction, or the logical 1 as being the current flowing in the other direction. But I can also have a superposition of the two. So you can actually have a superposition of current flowing in different directions. Probably the conceptually easiest one is just a simple atom that we've all learnt about in chemistry. We have a nucleus, and then we've got some different energy levels, and the electrons in the atoms can sit in those different energy levels. If I just choose one particular electron, which is able to jump back and forth between those energy levels, and I just select two such levels, and I can keep it constrained between them, then in principle, I can define a quantum bit like that. And so there's nothing unique about the way we build a quantum computer. There are all these different physical systems, and all of these ones here that I've drawn, they're all being actively pursued, because we don't really have any idea at this stage what the winner is going to be. It's far too early to tell. So we just know that there are all sorts of different ways that we can go about it. So maybe at that point, I'll just switch back to video mode and see you. So now I'm back in video mode. Hopefully you can see me. I should be able to see hand waving or anything like that. Did anybody have any questions or anything at this point? Otherwise I can jump back into it. No? Anisha, do you want me to continue, or?
Sure, yeah. If anyone has any questions,
Yeah.
just mute yourself, but yeah.
Yeah. Okay, cool. No worries. All right, I'll just continue in that case, and I'll share my screen again. Great. So you can see me again? Awesome. So let's have a look at what these quantum computers can actually be used for. What I've really described so far is what the basic building blocks are, and what sort of the conceptual differences are between classical and quantum computing. Now we want to know, how do I apply them? Because we sort of got the idea already that there are some significant constraints, because it's not just a simple matter of infinite computational speed up and getting all computations at once. So we immediately know from that earlier statement that actually these computers are quite constrained in what they're used for. They're not just applicable to anything. A common thing that people say is, oh, Peter, is this going to speed up my GeForce graphics gaming card? Am I going to get really, really cool, fast computer graphics? The answer is unfortunately no. None of the graphics algorithms that we're currently used, including these next generation ray tracing techniques, none of these are actually applicable to quantum computers. So unfortunately, I always have to disappoint people when they ask me how this is going to affect their gaming PCs. So one of the earliest known examples for what a quantum computer can be used for was called Grover's algorithm. That's just named after the fellow who invented it. And it's for searching databases. So if I give you a database that's sorted, in other words, like a telephone book, and I say, find my name, Peter Rohde, in the telephone book, that's a very easy thing to do because it's ordered alphabetically by name. If, on the other hand, I gave you the telephone book and said, my phone number is ... can you please find it? Then all of a sudden it becomes much more difficult because it's not ordered by phone number, it's ordered by name. And so if you have a database that's sorted, it's very easy to find something that you're trying to find. But if it's unsorted and effectively random, and in a phone book the numbers are effectively randomized, then really the best thing you can do on a normal classical computer is just start going one by one from page 1 of the telephone book and look through all the numbers until you find the one that's mine. And you can sort of see that on average you'd have to look through half the telephone book to find the number that you're looking for. So if you've got an unsorted database with n entries, then on average a classical computer has to ask the database n over 2 queries to find the thing that it's looking for. This Grover's algorithm speeds that up to only having to ask the square root of the number of queries. So if you had a telephone book and you wanted to find a telephone number and it only had 10 elements in it, then classically you'd have to look at, on average, 5 elements in the database. In the quantum computer, you'd only have to look at the square root of 10, which is 3.3, so that's not much of a saving. What happens if we go up to a telephone book with 1 million elements? Well, now, classically, you have to look at 500,000 elements of the database, but on the quantum computer, you only need to look at 1,000. Now we're starting to see a very big difference. What about if it was 1 trillion elements in the database? Well, then classically, you'd have to look at 500 billion elements in the database, whereas in the quantum case, you'd only have to look at 1 million. So you can see that these n over 2 and the square root of n, for small quantum computers, this doesn't make much difference. But once n starts getting big, these diverge quite rapidly. By the time we get to 1 trillion, the difference between 1 million and 500 billion is very, very substantial. And so this was one of the early quantum algorithms, and it has lots of applications. But this factor of square roots, that's called a quadratic quantum speedup. So the quadratic just meaning because it's a square root. That's actually pretty poor by comparison to some quantum algorithms, whereby you can get what's called an exponential speed up. In other words, you can exponentially reduce it. So if, for example, you had something that took 2 to the power of n classical units of time to compute on a classical computer, it would only take n units of time on a quantum computer. That's what exponential would mean. And there are some quantum algorithms that achieve that kind of scaling, which is even more dramatic. Here's an example of something to which that database finding algorithm from Grover can be applied. The way it's applied is a little bit technical, but it can be converted to this sort of problem called optimization problems, and these are really common. So suppose that you're Alice over here, and you want to get home, and you've got this road network in between you, and the A, B's, C's, and D's, those different nodes represent intersections, and the edge numbers here represent how long it takes to drive along that road. And then you want to ask Google what's the quickest way to get from Alice to Alice's home, or Bob wants to ask what's the quickest way for Bob to get to his house. So for Alice, it's pretty obvious. She'd go this way. And for Bob, it's pretty obvious he'd go this way. That has distance 1 plus 1 is 2, whereas that one has distance 2.5. Now, if only Alice or Bob ask that question one at a time, it turns out that classically that's a very efficient optimization problem. It's a really easy one to solve, and it's basically what Google does when you ask it to find you the directions back home. It uses this algorithm called the shortest path algorithm, which classical computers can handle really easily. When there's one user, just Alice or just Bob. However, suppose Alice and Bob are asking this question at the same time, and now there are conflicts. And the conflict is this one, that if two people try and use this intersection at the same point in time, they can't both pass through. One of them has to wait at the traffic lights, and there's a penalty associated with that, and we'll just arbitrarily make it 2. Well, now you can see that if I go through these different combinations, that in this case down here, if they were both to take what would individually be their shortest routes, there's a big difference between, it actually turns out to be cheaper that if one of them were to take an intentionally slower route, had they have tried to optimize it on their own, versus competing at that central intersection. So if they tried to compete, it'd be 1 plus 1, 1 plus 1, and then the penalty of 2 from the traffic light weight, which is a total weight of 6. Whereas if Alice intentionally sacrificed and went the longer way home, then they don't have that conflict in the middle. And now it's just 1 plus 1 and 1 plus 1.5, which is 4.5, and so it's less. And so this is called an optimization problem, or a multi-user optimization problem, where there are now constraints. And here the constraint is that there's a conflict penalty in the middle. Once we start increasing the number of users, this becomes a really, really hard problem that classical computers cannot solve very efficiently as you increase the number of users. So for a single user, you can do this really well. That's what Google does at the moment. But to do it properly, you want to look at a global optimization where you consider all of the different users at once, rather than just a single user optimization where you don't. And they can give very, very different optimization outcomes. And these sorts of optimization problems apply to all sorts of different things: traffic networks, scheduling of public transport system, flight path routing, supply chain networks, which gives us huge efficiency effects in the overall economy, the allocation of radio and cellular spectrum across different cell towers in the local network. And these sorts of optimization problems can be applied to this Grover's algorithm that I mentioned before, to get sort of quadratic speed up. So that's one example where quantum computers can help. Another one that people are talking about a lot is in things like drug design, where we want to simulate things like biological interactions, but way down at the molecular level. Now, at the moment, people do biological simulations at the molecular level all the time in genetics and molecular biology, but they do it using classical approximations where, for example, you approximate a molecule, a big complex molecule like the one down on the bottom right, just by looking at its overall sort of electric field distribution. And from that, you get an idea of how different molecules are likely to interact one another based on the attraction or repulsion of electric fields. But to actually do it properly, because these are quantum systems and they interact in a quantum way, you really need to do a quantum simulation. Classical computers can't handle that. This is an example of a problem where simulating a complex molecule grows exponentially with the number of atoms that are inside it, or the number of molecules that you're trying to simulate interacting with one another. But quantum computers, that's not the case. And they can very, very efficiently simulate these sorts of systems. And this is one of the examples where you can get a genuine exponential speed up as opposed to the earlier quadratic speed up. And it's just because, sort of intuitively, what we do is we say, let's just information theoretically represent this molecule down here on the right, just represent its whole structure, mapping it directly to a quantum qubit representation, and it just creates a one-to-one sort of direct mapping between the two. That's sort of the basis for why it becomes an efficient representation with quantum computers, which you can't do with classical computers, because within this molecule, the actual electron energy levels are all in highly superposition form. They're not just like classical apples. They're all quantum mechanical in nature. And so you map that across to the representation for the way the qubits represent those molecules. And of course, the obvious economic benefit and health benefit from this is pretty clear. If I can more accurately simulate the way molecular biology works or genetics works, then it means that you save having to do unnecessary trials, which take a long amount of time. The biggest time delay in drug design isn't so much coming up with ideas for drugs to try. It's actually the process of doing human trials on them. If I can just simulate them more effectively to begin with, I can cut down that process enormously. So this is one of the big touted benefits of or applications of future quantum computers, especially as we work towards personalized medicine, whereby we're not using medicines that are the same generically for everybody, but are targeted at your specific genetic profile. For example, we know that people with certain genes respond better to certain types of drugs, but we can be even more targeted than that and do it at a highly individualized level. Another application for quantum computing is big data analysis. So imagine you've got a huge data set like what Facebook has, your user database, where it knows everything about who you're connected with and what sorts of things you're interested in and what your friends are interested in and what groups you belong to. They have to extract all sorts of meaningful information from that huge amount of data, which of course is exactly what they do. That's what their whole profit model is. They want to extract useful data from that, primarily for the purposes of targeted advertising. But of course, as you know from the whole Cambridge Analytica debacle, it can be used for a lot more nefarious things than that. So how do we extract meaningful information from enormous data sets like that? Well, that can be enormously complex too, answering questions like how connected are different subsets of the data. Things like that can be really, really complicated and involve huge combinatorics using classical computational techniques. But there are some certain quantum techniques, such as quantum topological data analysis, where you're trying to understand the collective structure of huge data sets like this to extract something meaningful, which would require brute force using classical techniques. The really big one, of course, which is the original reason why we got so much interest from governments and why they started funding all of this stuff to begin with, is because it can crack certain types of codes. There's one particular code that quantum computers can crack called RSA encryption. And this encryption technique is used for what's called public key cryptography. And it's used basically by all of you every single day, including right now, whenever you log into the internet. And the purpose of public key cryptography, as opposed to more common, understood private key cryptography, is that in public key cryptography, you have two keys to encrypt or decrypt a message. One of the keys, called the public key, can only encrypt a message. The other one, called the private key, can only decrypt the message. So what I do is I make a public and a private pair of keys, and I make the public key public, as the name suggests. And then anybody can use that to encrypt a message, but nobody can use it to decrypt a message. So now, by publicizing my public key and keeping the private key to myself, anyone, even people that I've never met and I've never had the ability to meet in a secret dark alleyway to exchange a key with, they have the ability to secretly send me a message, and everybody else can do the same. And that's why you can log on to a server like Google, even though you've never gone and personally met them before. And so this is really important for the internet today. Now, the reason that this RSA encryption works is because it's computationally, at least using classical computers, effectively impossible to figure out what someone's private key is if you know their public key. And of course, if it was easy to find out the private key from the public key, well, then it would be pointless. Everybody would be able to read each other's message. So how does that come about? It's based on what's called the factorization problem. If I give you two really, really long integer numbers, say two 1,000 digit numbers, and I multiply them together, that's a really easy thing to do in that direction, multiplying them together. But if I give you the product of those two numbers and say, tell me what those original factors were that you had to multiply together to get that product, it turns out that classical computers can't do that as you make the number really, really large. So this RSA encryption exploits this. What it does is it says that the private key is those two original numbers before you multiplied them together, and the public key is the product of them. And you can use the product of those numbers to encrypt a message, but you need to know the original factors to be able to decrypt the message. And classically, we can't do that factoring process. However, there's a quantum algorithm called Shor's algorithm, which provides an exponential speed up for that exact problem. And what that means is that if today someone had a large quantum computer and they could use that to apply Shor's algorithm, they could take the public key that you use for communication with WhatsApp or whatever, and is publicly available. They could factorize it and immediately know what your private key was, and then read all of your messages. And so you can immediately see what the interest in that is to both good people and bad people, but primarily bad people. So having given an overview of why these quantum computers are really interesting and useful and what some of the benefits of them are, the big question is, why don't we have them yet? And of course, we all keep hearing about these headlines in the article, in the news about, for example, the Google's quantum supremacy result. I'm sure lots of you saw that in the newspapers. What's so different about building these compared to normal microchips, for example? Well, the reason is that classical computers use this digital information where things are just 0 and 1. And digitization effectively prevents errors. In other words, if I say a particular voltage is a 0 and another voltage is a 1. If it's voltages are actually analog, so if I say that a logical value of 1 corresponds to 5 volts, then my circuit just says, well, if it's 4.9 volts, that's close enough, I'll call it 5. And so this digitization sort of rounds things to the nearest, an analog value to the nearest digital value, and therefore prevents errors. But a quantum computer is very fragile because not only it's not just a digital unit of information, it can be in these arbitrary superpositions, and it's not at all discrete, it's continuous. It can have an arbitrary amplitude across this huge number of different elements in the superposition, and this makes it very, very vulnerable to noise. So if you consider this figure in the bottom right-hand corner, imagine that I've got my simple atom model of a qubit with two different energy levels. Well, how does an electron transition between energy levels? Well, what it does is that if it absorbs light of a frequency that has energy equal to the difference in those energy levels, it will cause that electron to jump to to that next energy level, or in reverse, it can reduce in energy level and emit a photon. So you kind of see that this atom, if I'm going to use that as a quantum bit, that needs to be pretty well shielded from the outside, because it's not hard for a single unit of light to come in and cause that electron to jump around unnecessarily and get completely stuffed up, especially if I've got a huge number of them. And for this reason, we need quantum error correction, which is something that we also have in classical computers. We have classical error correction, but our quantum error correction is quite different, and it makes things much, much more complicated, and it introduces huge overheads. And so this is really the reason why, for those of you who've read about the quantum supremacy results from Google, why that, even though might in principle do something that a classical computer can't do, it's not nearly capable of doing what I mentioned way back, which is this idea of a universal computation, because it doesn't have this capability to do error correction. What that Google results does is a very, very specific problem, which doesn't have error correction. It's a problem that isn't actually useful for anything practical, like any of those algorithms that I mentioned before can't be done on that quantum Google result. So this is really the biggest obstacle, is scaling these systems up so that we have error correction, so that it becomes scalable for a large number of qubits. So where are we at the moment? We're using optical quantum information, which is sort of my area of research. The best that people have got at the moment is sort of around about 20 photons. Google's chip had about 50 qubits. There are all sorts of other architectures, in that kind of ballpark. But at the moment, all of them have way too much noise and are far too architecturally constrained to be anywhere close to being universal, and therefore able to do those really interesting algorithms that I mentioned before. So when you read some of these slightly hyped up articles about we live in the quantum era and we have quantum supremacy, just remember there are some significant caveats associated with that. Technically, it's true, but for practical purposes, it's not. But what that result does show us is that it's advancing very rapidly. Now, I also wanted to talk briefly about quantum cryptography, because I told you that quantum computers can break some classical cryptographic codes. It turns out that quantum physics can also be used to make cryptographic codes that even classical computers can't, even quantum computers can't break. Now, there's only one perfectly secure encryption scheme classically, and it's called the one-time pad encryption scheme. And the way it works is this. As with every encryption scheme, you have a plain text message, the thing you want to send, and we're going to imagine it's a binary string of bits. And you also have a key, which is used to encrypt it. Now, for the one-time pad, the key is exactly the same length as the message. And then your encrypted message, called the code word, is given by the bitwise exclusive OR of these, sorry, I'll go back a bit, of these 2 bits. So this thing here means the exclusive OR, and the way it works is this: is that 0 exclusive OR 1 is equal to 1, 1 exclusive OR 0 is equal to 1, 0 exclusive OR 0 is equal to 0, 1 exclusive OR 1 is also equal to 0. Okay, so basically what that means, if you look at that as a truth table, is that if the first bit is a 1, then it flips the second bit, otherwise it doesn't. Now, you can see that if that key is just chosen randomly, then basically what that does is it goes in and it completely randomizes every corresponding bit of the plain text message, and then you can very easily prove that in the absence of knowing the key, it is technically impossible to know what the plain text is if I only tell you what the code word is. But the reason this is called the one-time pad is because this encryption scheme can only be used for a given key once. You can't reuse the key, otherwise it actually starts to become trivially crackable. And what that means is that it's not practical at all because it means that you can only use the key once. It's the same length as the message, and therefore you might, if you had the ability to share the key, you might as well share the message to begin with. So what quantum cryptography does is it gives us a way to securely share long random bit strings between two remote parties. And it's based on a combination of the superposition principle and the measurement collapse principle. And the basic principle is this: if I have a photon, for example. So I guess you're all familiar with the idea of polarization of light, sort of the angle, the axis of the angle upon which it propagates forward. Your sunglasses work by filtering out a particular polarization. So this is what we would call vertical polarized light. This is what we would call horizontally polarized light. This is what we call diagonally polarized light. And this is what we call anti-diagonally polarized light. Now, the way it works, the rules for the way these measure, is that if I prepare a photon into either horizontal or vertical, and then I measure it by asking, is it horizontal or vertical, it'll tell me with certainty whether it was horizontal or vertical. If, on the other hand, I encoded the photon as either diagonal or anti-diagonal, and then asked the question, is it horizontal or vertical, then I get complete random noise. However, if I ask the question, is it polarized diagonally or anti-diagonally, then once again, I'm guaranteed to get the right answer. And the reason for that is because if I ask the question, is it horizontally or vertically polarized, the measurement device perceives a diagonally polarized photon as being a superposition of horizontal and vertical polarization, and therefore it randomly collapses to one or the other. So, combining those simple rules, what I do is I randomly prepare a whole bunch of photons, and I randomly choose the basis, in other words, horizontal, vertical, or diagonal, anti-diagonal. I randomly choose those, and within each basis, I randomly choose whether it's either horizontal, vertical, or diagonal, anti-diagonal. So I end up with this long string of Alice sending random polarized photons to Bob, and then Bob is randomly measuring them in these different bases, anti-diagonal, diagonal, horizontal, vertical. And the point is that when Bob's measurement basis corresponds to Alice's encoding basis, then they're guaranteed to have consistent bits. And if they choose different outcomes, then they're guaranteed to have completely randomized rubbish. We want them to have consistent bits so that they have a shared key. So they do this over and over again, many, 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 many times. And then afterwards, they just openly talk to each other, and it doesn't need to be a secret. And Alice just says, okay, so for all of these different bits, these are the bases that I encoded in. And wherever Bob agrees, he keeps those bits, like these ones down here, and wherever he disagrees, he throws them away. And then what's left over is a reduced set of bits where they're completely random, but nobody in between could have known what they were, because if they did, they would have had to have measured them, and that would have collapsed them, and then they'd be able to detect the inconsistencies. So we can talk about that a little bit more, because that was a very quick overview. But the Chinese, they did an experiment demonstrating this using a slightly different version of that protocol, using a satellite recently. They did it using quantum entanglement, where they shared an entangled pair of photons between two distant ground stations a couple of thousand kilometers apart in China, and used this to share a secret key between those two ground stations, and then they were able to securely communicate with one another. So this is an example of a quantum technology which, unlike quantum computing, is actually becoming completely viable today. You can buy commercial devices today that let you buy two end-to-end boxes. You connect them with a fiber link in between, and using fiber, it'll do quantum key distribution like this. But it can do other things like quantum teleportation, which I was going to talk about, but I think I won't because I'm running out of time. So maybe at that point, I'll switch off and go back to video mode since I've just looked at the time, and we can, whoops, sorry, there we go. Great. And so maybe at this point we can open to Q&A and go back to anything that anyone had questions about, given that, now I can see that there are some questions. Okay. Okay, cool. Let me start. Can you guys hear me? Anisha?
Yeah, we can hear you.
Okay, cool. Okay, so I'll just start by reading what's written in the chat here. So from Pranav, how will quantum encryption affect other encryption styles like AES? Right. So AES is a private key crypto system, meaning that you use the same key for encryption and decryption, unlike the RSA one. So it's used for different purposes. But the answer is that quantum computers, to the best of our knowledge, will not significantly compromise good private key cryptography like AES. Basically, the way it works is that private key crypto systems like AES, they can be slightly improved using that earlier algorithm that I mentioned called Grover's algorithm. And that gives a quadratic improvement. So the way to think about it is this: if you're going to do a brute force attack on a private key crypto system like AES, the way to do it is just by systematically trying all the different keys until you can decrypt it to something that works. Okay, so on a classical computer, if you've got a key with 512 bits, then that's 2 to the 512 combinations of keys that you could, in the worst case, have to try out before you successfully brute force crack it. That Grover's algorithm lets us treat that as one of these unsorted search problems. So it effectively reduces it from 2 to the 512 choices of keys to the square root of that, which is the same as 2 to the 256 possible keys. So effectively what Grover's algorithm does is it cuts the key length in half in terms of the complexity or the number of computational time steps that it has to do. So it would take AES 256 and make it the equivalent difficulty as AES 128. But that's not a huge problem. It just means that we double our key lengths to begin with, and we bypass that. We don't get the exponential speed up as before. So I hope that answers Pranav's question. On to Jamie. Will PsiQuantum or similar project catapult the 20-photon quantum computers of today to millions of photons? Yeah, so PsiQuantum, I know those guys very well. Their intention very much is to go towards the millions of photons and qubits. They're very secretive. We don't know exactly what they're doing, but certainly they absolutely have to go beyond 20 photons, and their goal is to go to this millions of qubits regime with error correction. They're very, very secretive. They're operating out of Silicon Valley. Nobody really knows exactly the mechanisms that they're using. Needless to say, it's incredibly challenging to have millions of photons, but that is my understanding of what their goal is. When and if they'll achieve it, I can't possibly know, because they're really quite secretive. But obviously investors have a lot of confidence in them because they just raised about $250 million in venture capital funding. On to Subodh. What's the largest number to be successfully factored? Okay, so yeah, the next answer is right. I think it's about 15. It turns out that it's not just as simple as how large the number is. It's about what the nature of the factors are. So factoring the number 15 into 3 and 5 is just as complicated as factoring numbers that have that same periodic property. So like multiples of 3 and 5, sort of in a rough, vague, intuitive sense. But the answer is right. It's a tiny number, one that you can do in your head. So don't feel threatened by quantum computers cracking your public keys at the moment. But yes, to actually compromise RSA, they're going to have to factor numbers that are thousands of digits in length. Great, glad to hear that, Pranav. From Redimson, you said that if RSA, classical RSA has 512 bits, can it be factorized using a quantum computer on 8 qubits? No, so it's not quite as simple as that. If you want to factor using Shor's algorithm, it doesn't just require a number of qubits necessary to encode the input 512 bit number. You still, whatever that input number is that you want to factor, obviously that has to be an input, so you have to have at least that many bits at your input. But there are all sorts of extra overheads, and much of it comes from, ultimately, when it happens, will come from this error correction. The layers of encoding that we have to put over the top of an elementary quantum algorithm to make it actually robust against errors and functional is significantly more than just that starting base number. So it's not just as simple as, if I want to factor a number that's this many bits long, that I need that many bits in my quantum computer. Going on to Felix, student of photonic quantum technology here at University of Vienna, looking towards different landscape of computing architectures, communications, encryption, etc. Any tips how to orient myself to find a path to go deeper into a specific area? Any area recommended? Any approach for the current developments? Yeah, so for those of you interested in getting into this field, you've probably gathered, just despite the fact that it wasn't a very technical talk, that it is a very, very technical field, and it sits at the intersection of various different areas. It sits at the intersection of mathematics and theoretical physics, but specifically quantum physics and computer science and engineering, if you want to go into the experimental side or the theoretical side. So if you want to move into these areas, then those are the basic areas that you will want backgrounds in, but particularly the mathematics and the physics will be necessary. Engineering is helpful, but I guess the answer really depends a lot on how you want to target it. So if you want to have a private chat at some time, any of you, about a specific area that you might be wanting to get into, we can feel free to get in touch with me. My email address is there, and you can all feel free to reach out to me if you want some tips on how to target yourselves to get into this field, because it's really booming. So from Paulo, when you say error correction, you mean when applying the same error correction techniques to the measured qubits as you applied to the classic qubits? No, the last part of that sentence is correct. There are specific error correction techniques for qubits. It's not as simple as the error correction techniques we use for classical computers. In fact, within the CPU in this computer that I'm using now, the processor itself isn't really using any error correction at all. Really, the digitization is sufficient for the error correction, just taking the analog electrical signal and just snapping it to the nearest value. That's sufficient for what's going on inside this computer. But then it becomes more problematic when you do long distance communication, where noise is more problematic. But with quantum bits is different, because you don't want to just snap things to the nearest superposition. That's exactly what you don't want to do. That's what a measurement does. If you take a superposition of two values and you measure it and it snaps it to the nearest thing, well, that destroys it and completely undermines the whole thing. So actually, the error correction techniques need to preserve the superposition structure of the information. not just what those basic logical values are. And so they are completely different techniques altogether. Conceptually, some of them are kind of overlapping and will make some logical sense. But more generically speaking, they're completely different in the way they operate. On to Dixon. Would it be possible to put a qubit in a superposition more than just binary, like 0, 1, 2? Yes, absolutely. Quantum systems in general can have arbitrary numbers of states. What you're talking about there even has a name. It's called a Qdit. So instead of a qubit, you have a Qdit, where D refers to the dimension of the system, and D can be arbitrary. So you could have an atom with 100 different energy levels, and the electron can be in any of those 100. Then it would be a 100-level Qdit. However, computationally, it doesn't really make any difference whether you use qubits or Qdits. It doesn't cause any sort of exponential gain or anything like that. In terms of the overall computational benefit, there's no real reason to use one or the other. It's just that it's simpler to formalize things in terms of the simplest possible units of information, because then it means that our gates are as simple as possible. From John, which universities currently have the best curriculum for training students to design and develop software to run upon quantum computers? Yeah, so that's a very big question to ask. There are lots of universities doing this. Speaking on behalf of where I am here in Sydney, we recently started the Sydney Quantum Academy. You can look it up. It's called sydneyquantum.org is the website. And what it is, it's a unification of 3 universities in Sydney working towards a joint unified teaching program and research program for both undergraduate and postgraduate. And it's only, yep, that's correct. The one that you just typed there, I think that's correct. And they're building up a training for all different levels, both undergraduate, postgraduate, research programs, studies programs, targeted for people that want to enter the industry at different levels. So that's sort of how it's working here. Lots of places around the world are doing similar kinds of things. I don't know what all of their individual curriculums are, but that's basically what's going on here, and I can tell you more about it if you reach out to me afterwards. These error correction techniques, relatively easy to understand. Some of them are easy to understand. If you want to look up one that's easy to sort of understand, I'd recommend looking up a paper called the 3-qubit code. You'll be able to find this if you just do a search around on the internet. The 3-qubit error correcting code for quantum computation. That one is the one that is most sort of analogous to the way a classical error correcting code would work. But in general, it actually becomes, some of the really modern quantum error correcting codes are really, really abstract mathematics. Great. So is that it?
You can take the last question. There's one more, I think.
Yep. Sorry, did I miss one?
Yeah, there's a question from, oh, no, there isn't. That's it.
Yep, okay, great.
If there's anyone who has any last questions, you could ask them right now. Or if not,
otherwise, as I said, you're all welcome to email me.
Of course.
My email address should be on the, so my email address is what you just wrote, drrohde@gmail.com. So I'll just type it in.
We can also send it out with the recording and the, we can send it out after this as well.
Yeah, and I also promised the community team that I'd share my slides with them, so you'll all be able to access those afterwards as well.
Yep. So thank you all for coming, and thank you, Peter, for hosting it. He woke up at 4 a.m. for this, so that's and it was still really comprehensible and really, really interesting. So stay tuned for some more updates from Q-munity, and if you have any questions, you can reach out to us or reach out to Peter directly. I'm sure he'd be more than happy to answer anything.
Great. Thanks a lot, guys. Good to see you. And thanks, community team, for organizing this. I think it's a fantastic initiative, and I'll try and encourage my colleagues around the world to support you guys.
Yeah. Thank you.
Great. Cheers, guys. See you later.
Thank you.